Alrighty. Hi, everybody. Welcome to the May edition of the Cells of Society seminar. I'm Andrew May with the UVM Extension Center for Sustainable Agriculture, and I help to coordinate this series along with Chris Callahan and Hans Estrin. Today, our topic is maple. Our theme is maple. And we're excited to have two great speakers with us. The presentation will be a joint presentation between our two speakers titled From Tree to Bottle, Impacts on Maple Syrup, and we'll have Mark Isselhardt with the UVM Extension as a UVM Extension Proctor Maple Center. He's a maple specialist, and Abby Vandenberg, a research associate professor in the Department of Plant Biology at UVM. A bit more about Cells to Society seminars. Our overall goal is to promote connections, transfer of knowledge, transdisciplinary collaboration, effective leverage of research findings, and the identification of new research questions for collective impact. So this seminar series is meant to be an opportunity to promote collaboration and ultimately to weave a stronger network of relationships and professional connections. So here's the team currently working on putting our seminars together. So thanks again to Chris and Hans, as well as Kathy and the rest of the media team. And as I said, this is a collaborative effort, so please send us your suggestions at the link at the bottom of the slide at go.uvm.edu/Cells of Society seminar, where you can also view the schedule and past recordings. So the way that it works is that we have monthly virtual seminars. The seminars, including the one you're seeing today, is designed to be an opportunity to share research, education, and work within cows and beyond. So these seminars typically have two speakers. And then we have quarterly out-of-the-box brainstorming sessions happening every 3 months or after every 2 seminars, where we select multiple emerging themes and potential new projects and discuss them in small groups. And the out-of-the-box sessions are much more engaged and interactive and collaborative and surround themes and project brainstorming to hopefully create some new grant proposals as well. So standing schedule is every second Thursday of the month at 2 p.m., which will occasionally change. So again, take a look at this at the website and submit any topics or theme ideas that you have at that same link. And so finally, as we've mentioned, just visit this website for more information. You can also link to YouTube recordings of all of our seminars that we've been putting on for the past almost a little over 2 years now. So yeah, take a look at all of those anytime. And with that, I believe we're going to start with Abby. So I'll pass it over to you. Take it away.
Thank you very much. And thank you for having us today. This is an awesome opportunity. As soon as my computer catches up here. All right. So yeah, fantastic. So when with the topic at hand, when Mark and I first started discussing the topic maple syrup quality from tree to table, so much of our work is covered under that umbrella. We have so much to talk about, our research and extension work that falls within that area. It was kind of hard to choose. So what we decided that we were going to do today is actually literally go from tree to table and start with some of the science behind the ability to collect sap and maple syrup, and then go into some of the quality issues and what quality is even. So we'll cover a lot of ground today, and hopefully it will be something new for everyone. So basically, you all live in Vermont. I'm making that assumption, but I think everyone in this room lives in Vermont, and we all probably have a fairly decent idea of the basic process of maple syrup production. We know that we drill holes in trees, collect sap, boil it down, and at the end of the day, we end up with this fabulous, yummy product that everyone loves so much. But when you kind of stop to think about it, there are some interesting questions if you just dig a little deeper that are raised in your brain or potentially raised in your brain. For example, Why is it that it is the Vermont and the Northeast that's so well known for maple syrup? So there are maple trees all over the place. You can find red maples in Louisiana and Florida. So why isn't there Louisiana maple syrup? And then another flip side of that question is, why is it maple? So why aren't we doing this with every forest tree species? Why aren't we making oak syrup and cypress syrup? And the answer to those questions, if they've ever occurred to you before, have to do with the actual science behind the physiology and anatomy of the sap flow and syrup production process. And that's what I'm going to go over in the first part of this talk today. And I put this picture in here because I absolutely love it. These are some of our predecessors at the Proctor Center, and they are measuring the pressure in maple trees. And this is really not far off from some of the measurements and experiments and even the instruments that we would use and are using today to answer some of these questions. So I just love to start it off that way. We like to say often nothing new under the sun in maple, and sometimes with maple research that is actually very true. Okay, so the ability to collect sap and maple syrup, collect sap and make maple syrup is possible due to two unique properties of maple trees themselves. And this is the ability of maple trees that they have to generate positive pressure in the xylem sap. This is actually what allows sap to flow, but I'll get into that in a minute. And the second thing is the relatively high concentration of sugar in the spring xylem sap. This is also something very unique to maple. Essentially, if we're going to collect and harvest and make a sugar product, there has to be some sugar there to begin with. So these two foundational things are what allow this entire process to happen, and they are fairly unique to maple trees in the genus Acer. Underlying those two things is that we also have to have the right weather conditions for these things to happen. So we need to have nighttime temperatures that are below the freezing point of water, followed by daytime temperatures that are above the freezing point of water. This is what actually enables that positive pressure to generate, which we'll explain in a moment. But this is fundamentally the reason why, even though we have maple trees growing all over the place, we don't see maple syrup or much maple syrup made in Louisiana, where you simply don't have these weather conditions, especially during the dormant season. And so for those of you, I know there's a range of disciplines in this room, but all of us, I guarantee it, at least in high school, had high school biology. And I'm fairly certain that in all of our high school biology classes, what we learned about how things move through plants is that generally the transport tissue that we're thinking about when we think about transporting carbohydrates or sugars around the plant is the phloem tissue. And for some of you that are really far out of high school biology and that haven't thought about a plant in 100 years, this is probably ringing a few bells. And generally, the xylem tissue is what we think of in terms of transporting water and mineral nutrients from the soil water up through the roots and out through the leaves in the transpiration stream. Generally speaking, it is not xylem tissue that we are concerned with when we are talking about moving sugars around the tree. Yet I just emphasized that, oops, wrong way, that it was the xylem sap that we are harvesting this sap from. So harvesting the sugary sap from. So what gives here? Have we turned plant biology on its head? Are we violating the laws of physics? And the answer, of course, is no. The big difference here is that these general characteristics of plants that we're thinking of are characteristics that have to do with plants during the growing season, when trees have leaves and transpiration is occurring. The period of time that we're dealing with, the trees are in a period of winter dormancy, so they don't have leaves. And during this period, there are a lot of different things that go on in plants that we don't normally learn about in basic biology and basic plant biology classes. So let's get with the sugar part. So this is actually the soluble sugar concentration in the xylem sap of a dormant sugar maple tree across basically during the leafless period. So you can see here, this is from November through May. So this is basically from leaf drop to leaf out. And so even though typically xylem sap is just water and mineral nutrients during the growing season, during the dormant season, especially in sugar maple and maples in general, there is a relatively high concentration of sugar in that sap. And you can see that it is there sort of the entire time and then actually spikes to be quite a bit higher as the tree exits dormancy and begins to prepare to resume growth. And so the sugar is here for a lot of different reasons. It's helping to provide freeze tolerance. It's helping to provide some fuel for the tree as it exists during the dormant period without leaves to photosynthesize. So there are a lot of reasons that it's here. And we assume that we can make some assumptions about why it gets higher in the spring, that it might have to do something with the resumption of growth, or might have something to do with mechanisms to reduce embolisms and restore the water transport system. But that is something to discuss a little later. But essentially, the important thing is that there is actually a relatively high concentration of sugar in the xylem sap of maple trees over the dormant season. And this is not something you find in most other tree species. Okay, and so this is a little bit of where we're collecting that sap from. So this is a cross section of sugar maple wood. And so you can see here are the large xylem vessels, and this is where the sap that we are collecting, the sugar-laden sap that we're collecting is located. And typically, again, that will be something we associated with water transport through transpiration. But during maple sap collection, it is these vessels that have the sugary sap that's being collected. You can also see here that surrounding the vessels are fiber cells. These are cells that provide structure and strength to the secondary xylem, the wood. And then also, although we tend to think of, and again, something kind of beaten into our heads as biology students, is that wood is dead and not a living tissue. But there's quite a bit of living tissue in xylem and in secondary xylem and wood. And one example of this are array cells. These are living cells, and these are the cells that actually are where starch is stored in the wood. And what happens is that starch gets converted to sucrose and loaded into these xylem vessels into the sap, and it is ultimately that sap that we harvest. And so that takes a little bit care of the sugar picture, as it were. So let's talk about that freezing and thawing temperature thing. So we know that freezing and thawing temperatures are required, and we're harvesting sap that's in these vessels. So again, if we think a little deeper about this, we all kind of know what happens when water freezes. Many of us have probably had an accident like this that happened in our own freezers. Water expands when it freezes, ice expands. So if you imagine that sap sitting in those vessels as a liquid and then it freezes, the question that arises is, well, why isn't it like kind of exploding out of those xylem vessels as it expands and freezes? Or is again, like, are we violating the laws of physics, or, what's going on here? And it is true, like the water and the ice is going to expand in the vessels, but the reason it doesn't cause damage or it doesn't explode out of the tree also has to do with the very unique anatomy of sugar maple wood. So this is another cross-section of sugar maple wood. This time the vessels are running up and down. You can see the ray cells there where the starch is. And so in most tree species, many tree species, the fiber cells that are surrounding the vessels are also liquid filled and part of the water transport system. But in sugar maples and a few other species, those fiber cells are actually hollow. They're gas or air filled, so that when the sap in the vessels freeze, it actually has some place to expand. And again, so here is a lovely depiction that was generated by my former colleague, the UVM's previous maple extension specialist, Tim Wilmot. So this is a lovely depiction of what is going on inside the trees. And we're especially talking about up here in the fine branches of the tree, where they're going to be the most sensitive to those temperature fluctuations, just because of thermal mass. So here you have a xylem vessel, liquid filled. This is when the temperatures are above freezing, and it's surrounded by those gas filled fibers. And when the temperature is above freezing and it's the dormant season, like literally nothing is happening, or essentially nothing is happening. So the real action begins to happen when the temperature begins to go below freezing. And at this point, the vessel, the sap in the vessels, especially in those fine branches, begins to freeze. And in doing so, the first place we see ice is as frost on the outsides of those neighboring air-filled fibers. So once those ice crystals begin to form on the surfaces of those neighboring fibers, essentially, as the temperatures stay below freezing, those ice crystals will continue to grow and grow and grow and grow. And as they're doing that, they are being fed by the water, the sap, in the neighboring xylem vessel. And this ice crystal growth is a force that is large enough, and with the cohesion and tension of water, that is generating enough negative pressure or tension to draw up water from the soil through the roots and up to those fine branches where those ice crystals are being formed. And this is literally essentially the exact same thing that we see in transpiration, only in transpiration, the driving force that's driving that water uptake is the evaporation of water from the stomata in the leaves. In the case of dormant maple trees, the driving force of water uptake is actually the freezing of water in those air-filled fibers. And so this water uptake process will continue with water being drawn up and up and up and up until the temperature has stayed low enough for long enough that everything freezes solid. And when this happens, things can remain like this for days and even weeks at a time, and essentially nothing is happening at this point. So the second part of the action, of course, then begins to happen when the temperatures go above freezing. And as that happens, a couple of different things start to happen. We have, first of all, those ice crystals begin to melt. And the gas bubble in those fibers that has been compressed by those ice crystals also the gases begin to warm and expand. So there is some element of a little bit of pushing pressure from the fibers into the vessels, or the sap in the vessels. But the other main thing that's happening here is that as the temperature transitions from below freezing to above freezing, enzymes kick in that are triggered literally by that transition from below freezing to above freezing that begin to convert that starch into sucrose, and that sucrose is then loaded into the xylem vessels. So now you've got sucrose being dumped into that xylem sap, which is causing another osmotic gradient to happen, further causing the water from the air, the melting water from those fibers, to be drawn into the xylem vessels. And then the third factor you have going on here is kind of relatively simple. The tree has brought up an enormous amount of water against the force of gravity. So all of those things functioning together generates a positive pressure, and actually a rather enormous positive pressure, or above atmospheric pressure. So here is a figure showing the temperature and pressure in an intact maple tree at about trunk height across a couple of days during the maple production season. So you can see here, when the temperatures are below freezing, the pressure is below atmospheric. That means uptake is happening. But then you can see that as soon as the temperature flips to above freezing, that temperature spikes up to almost about 30 psi, or it can be as high as that, just under that level, which is essentially close to the pressure in many car tires. So it is a fairly substantial amount of pressure that has been generated by some physiological processes and some anatomical features that are bringing that water above against gravity, adding the osmotic gradient, everything together, making an enormous amount of pressure. And that pressure will decline over time as the sucrose is basically as water moves around the plant. And it will decline until another freeze event happens, and then the entire process starts over again. And it is literally that process that we as maple producers totally depend on it's the foundation of our maple production season, and it is the foundation of why we are so interdependent on the really subtle changes in temperature fluctuations that happen during the season. So now, many of you are probably here, but just in case, why we need to answer the question of why does this have anything to do with why sap flows when we put a hole in the tree? And of course, most of you are already here. The answer is this is because the sap or the tree has created an internal environment where the pressure is quite a bit higher than the atmospheric pressure outside of the tree. And just like in every other situation, water is always going to move from a region of higher potential to lower potential, or we can say in this case, higher pressure to lower pressure. So when we put a hole in the tree, the sap is going to flow from the inside of the tree to the outside of the tree until the pressures in the two regions are equalized. And essentially, this is why this can work with a maple tree. If you put a hole in a maple tree or another tree during the growing season, you might actually see water get sucked in. And if you go try and do this with an oak tree in the middle of the sap flow season, nothing will happen because it doesn't have the same mechanism. Okay, so now that we know a little bit about that, I have a few minutes that I will just briefly talk about the practice of maple syrup production, which I'm sure most of you are familiar with, but it will lead us into the quality aspects of the presentation that Mark is going to talk about. So basically, we collect sap by means as simple as drilling a hole, seeding a sap, and hanging a bucket. This can also be done with plastic spouts and tubing systems. And I'm going to go through a little fast here because I'm running out of time, of course. These tubing systems, if they're used, are generally like larger, small networks of rivers where you have smaller tributaries flowing into larger tributaries, ultimately to a collection point, which can be a sugar house where it's going to be processed, or it can be a collection site that's remote to the sugar house. But either way, oops, I'm going to skip a little bit ahead here. Because of that tubing system and because of the interconnection of that, many maple producers will choose to add vacuum to their tubing systems, which now that you understand more deeply the physiology and anatomy behind this makes a tremendous amount of sense. The rate of sap flow is always going to be dictated by the differential in the pressure between the inside and the outside of the tree. So that when we add vacuum, we are increasing that differential, which allows sap to flow at a higher rate, even in conditions, and especially in conditions where the the weather conditions, maybe they've been a little bit marginal at like a very small freeze with a very small or short thaw. This pressure inside the tree in a condition like that might not be as tremendously high as a long, deep freeze followed by an extended thaw. So in conditions like that, where we have just marginal conditions for sap flow, having the vacuum there maintains that differential at a level that can make sap flow more substantial under those conditions. So it is really a sort of a game changer, and contributes to about a doubling of sap yields, generally speaking, compared to just hanging a bucket on a tree. Okay, once we get the sap collected, it's going to be stored for as short of time as possible because it is 2% sugar. So it is a very nice place for microorganisms to grow. So we want to process it. You can kind of think of it like dairy. You want to process it as fast as possible. And so here we have it. The water has to be removed from the sap, which is, like I said, 2% sugar, to generate syrup, which is about 66% sugar. And the question is how? We have technology like nanofiltration and reverse osmosis that allows us to remove a lot of that water with selective membranes and pressure prior to any kind of other thermal evaporation, which can significantly impact the time and fuel costs associated with maple syrup production. It's a very effective tool for increasing efficiency and reducing costs. However, even though we have technology capable of concentrating up to that level, up to all the way up to syrup density at 66%, we can't use reverse osmosis for everything. And the reason for this is because the majority of the reactions responsible for maple syrup flavor occur only as heat is applied during evaporation. So we need to make sure that there is some heat involved in the process to ensure that we have the color and flavor that maple syrup is known for. All right, I'm going to skip Maillard reactions and we'll come back to this later, maybe if we have time. Basically, once we get to boiling, there are lots of different types of evaporators, from everything from wood to steam to electricity to fuel oil. And once that sap is, whether it's with RO plus an evaporator or just an evaporator, once it reaches 66% sugar, it needs to be filtered in order to remove solids that are precipitated out and make a clear product like this. And it is then packed into either larger drums or retail containers. And at this point in the process, it must be graded if it is going to be sold. So I'm going to kick it off to Mark from here. And Mark, I hope I set you up in a way
That's great, Abby.
Yeah, let me stop the share here.
Thanks. All right, let me share my screen. Start right away. So as Abby said, syrup has to be graded. And a lot of this has to do, there's actually quite an interesting historical context as to why we grade syrup. Part of it has to do with consistency. It wouldn't work very well to have a consumer go in the store and buy something, and then it could be totally different the next time they go in. So consistency of product is very important. But even before that, the standards for grading pure maple syrup are actually rooted in some of the early days of food safety and adulteration issues. It is said that in Chicago in the early 1900s, there was more maple syrup produced and sold than anywhere else in the country. And this is owing to perhaps some unscrupulous businesses who used mostly glucose or other cheaper sweeteners, a little bit of tinting with caramel color, and then calling it pure maple syrup. So the industry reacted to this unlawful behavior and chose to organize and get more rigorous grading standards that involve 4 key elements. We have grading standards at the federal level. We have them at the state level. There was a period of time when the standards were not harmonized across states and provinces. About 10 or 12 years ago, there was an effort by the industry to harmonize them so that the language and the standards were equal across all those producing regions. There's a lot of information digging deep into those details. What I do want to say is that given that this is a non-timber forest product that is made from a single ingredient, raw maple sap, it makes it very unique in terms of food production. We don't have a lot of options, and actually written into the standards, there are very few options. If you have a defect in quality, you can't remove anything that's naturally occurring, just like you can't add anything that wasn't there in a soluble form to begin with. So the standards are there to increase the rigor about purity and quality, and we're going to walk through all those different elements. The 4 standards of grading are color, clarity, density, and flavor. And some of those are quantitative measures, and we have instruments that, to a varying degree of accuracy and precision, can be used to measure them. Some things like perhaps flavor isn't so quantitative, and we fall back on experience and common terminology and language to describe what is a good quality flavor and what is not. Abby has done a great job in a lot of embracing more rigorous sensory evaluation techniques, and actually has been awarded a really significant grant to try to bring maple into sort of the modern era in terms of rigor when we talk about evaluating the sensory qualities of pure maple syrup, much like other food industries have done already. But maple's traditional and perhaps lag a little behind in those cases. If you're at all curious about the basics of grading, I have these grade cards that are available. You can scan those QR codes and go to them. I also have a short video describing what each one is. If you want to go really deep, you can go to what's a terrific publication that was just produced last year. Tim Perkins and Abby are both editors on this document. This is the 3rd edition of what's considered the Bible, or really standard reference for making pure maple syrup. That's the North American Maple Syrup Producers Manual. That's free as a download PDF, and there are some sources you can get hard copies. It was great to be part of this project. I was a lead author on the chapter about syrup filtration, grading, packaging, and storage, which is generally the chapter that talks about syrup quality. You can see some images there of syrup that didn't quite meet the standards, and we'll go through some of those issues. But if you're looking for a real deep dive, this is a great place to go. And as Abby had mentioned or alluded to, maple syrup is a non-timber forest product, and it's made just with a single ingredient, maple sap. But it's not just maple sap. It has to be exposed to heat and to have all those complex chemical reactions that occur between the sugars, amino acids, all the other flavor precursors that are in that raw sap. Those all have to get together and have all those complex Maillard reactions and caramelization reactions in order to get that color and flavor that's so characteristic of pure maple syrup. The other issue is it means that there can be quite a bit of variability. So it's not like baking. You can't say one day I want to make a very light syrup and tomorrow I want to make very dark syrup and then I want to go back to making some light syrup. The sap quality on any given day, combined with the processing techniques, really dictate what you're going to make on any given day. And there's a little bit of influence in terms of what a producer chooses to do in terms of sap collection methods or boiling methods, but they can't really go backwards and change once it's already been produced. And like I said, that's written down in regulation. Sap quality coming out of the tree has a huge part to play. And here's a picture of some sap going into a sap collection device called a releaser. This is the last day of boiling for this producer. And you can see, there's a lot going on microbiologically speaking. We have some yeast probably, perhaps some bacteria contamination. All of that will get boiled and denatured, but it absolutely has an influence on what the syrup quality will be. So generally speaking, over the course of an average sugaring season, you'll make lighter syrup in the early part of the season when air temperatures are cooler and there's not much going on in terms of bacterial or microbiological activity in the sap. Later in the season, again, a typical season, it gets warmer, you see sap becoming cloudy and you tend to make a darker syrup. Of course, very few seasons are average or typical, and so you can see a range, but the overall trend is light to dark in terms of what syrup you produce during the season. Just to highlight how important or how variable each year can be, this is some work that Tim Wilmot collected, some data Tim Wilmot collected. So along the y-axis, you have temperature, but then you can see 3 different years worth of data for, I should say, 2000 through 2003. What's important to take home here is that the blue line represents temperature and the horizontal black dotted line is 0 Celsius. So you have the freezing point right there. The deep or thick red line represents periods of sap flow. Now, just squinting your eyes a little bit, you can see sap flow does not turn on day 1, flow equally and steadily all throughout the season and then end at day X or whenever the season ends. It's made up of a few very discrete but very important sap flow events, which Abby did a great job outlining, all the physiology behind it. But you can say, there's a saying in sugaring, if you've seen one sugaring season, you've seen one sugaring season. Sometimes they come early and end early. Sometimes they They come late and end early, or some combination in between. And I start getting calls, well, in January, asking how the season's going to be. And what I'd really like to show folks is, look how variable this is. It's impossible to know for sure how the season's going to turn out. So the production practices that a sugar maker chooses to use has an impact on the sap quality. And this is a picture from a sugar bush in 1940 in Westmore, Vermont, using very traditional methods, a bucket. There were some horses involved, carrying sap from each individual crop tree into a collection tank, hauling it to the sugar house and boiling it. And this is really the technology that was used until really up until the late 50s, early 60s is when plastic tubing even became an option for sugar makers. So this is really how maple sap was collected, maple syrup was produced for much of the history of maple production in North America. Of course, people still use buckets. Unfortunately, they don't always adhere to the best food safety guidelines. It's really important that folks understand we are making a food product, and we're concentrating the sap down many, many times. And so anything that's not volatile, even things that are volatile, are going to be infused into that sap. So using something that's not food grade, like a garbage can, even a kitty litter, or a seemingly innocuous, very shiny galvanized trash can, those are not appropriate for food production, and they really shouldn't be used. You can still use gravity sap collection. Some people use tubing with no vacuum. Some people use food grade buckets. But the understanding is you really have to use food grade materials to do it. Tubing systems, as the plastic became more available and affordable, really was seen as a great innovation for maple. Interestingly, some of the original tubing systems weren't held up between each tree. They were actually laying on the ground. So you had a little line of tubing that went from the tap hole down to the ground. And actually, documents from predecessors in my position said, as long as it's downhill, it should be fine. And it is funny to think about, what we're saying now, what folks are going to be reflecting back on in 40 or 50 years, thinking that we were out of touch. But originally, tubing was not designed to increase production. It was designed as a labor-saving device. We saw a huge decrease across the U.S. in farming, the sort of a transfer from being an agrarian economy to one of more manufacturing and other activities. And we saw farm families getting smaller, and there's just less labor to go from tree to tree to collect sap. So tubing was really important in cutting down on those requirements. The basic tenets of tubing is tight, straight, and downhill now. You want to make sure that all that tubing is on grade. And if you don't follow those basic standards, you have a chance of sap collecting and pooling. And as Abby says, you wouldn't want to have milk sitting around heating up in the sun. So you definitely don't want maple sap either doing that. So poorly installed tubing systems can impact not only sap flow, but the eventual syrup quality. Some producers choose to use sanitation practices to try to mitigate some of this. And there's a decade worth of research that's been done by the folks at the Proctor Maple Research Center talking about the various techniques and how their impacts are on syrup quality, and then the final bottom line in terms of cost to implement those practices. A lot of folks will find that introducing any sanitizer is just too labor intensive and isn't done. But when you start to have an issue like in the picture here, folks are having issues with contamination in the tubing system. They tend to start to look for practices that might help them alleviate that. So once you collect that sap, you also need a place to store it. And here's a picture of one of the two new sap silos. Each is 10,000 gallons at the Proctor Maple Research Center sugar house. And you have all the sap sitting, but you need to boil it. It can't sit there for very long. The issue of quality degradation is quite real. And the same is true if you're a smaller size operation. Sap flows at these unpredictable rates and times, and you need to be able to boil it when you collect it. It's very difficult to hold on to sap. However, I will say that an innovation that they've done at the Proctor Center is introduce repurposed dairy refrigerated tanks to chill the concentrate. This is not raw sap because the volume would have to be so big of your storage, but the product of reverse osmosis is now at a volume that's kind of manageable for folks. And so they've used this refrigeration technique to inhibit microbial growth over a fairly long period of time. And that can help with labor and budgeting of time, but it also helps improve or reduce degradation of syrup quality as a result. One thing about syrup producers now, we know through survey data that over 70% of producers use RO, and even a higher amount of the total crop is exposed to this technology. So it's definitely widespread. We find technology, even for very small operations, are able to use this membrane technology. And the reason why it's so widespread is it significantly reduces the energy needs and boiling time. You're taking 75 to perhaps 80 or not even 90% of the water out of that sap before you have to use that really energy intensive practice of atmospheric boiling to make the finished product. The issue with concentration, however, is that it is now, if raw sap as it comes out of the tree is roughly 2% sugar, now you take it to 10 or perhaps 20 or even above percent sugar, that's an extremely hospitable environment for things to grow in. And so you absolutely need to process that sap as fast as possible. A little note about measuring instruments. So syrup has to be boiled to a set density. That's all laid out in the regulations I mentioned at the beginning. There are instruments that are used. The most common is a hydrometer, which is perhaps an instrument you're familiar with, a calibrated thin glass tube that's floated in the liquid and used to characterize the apparent density of that liquid. What we found in doing some work just in the lab is that very, very small differences in the weight of that calibrated hydrometer can have a huge difference in the apparent density of pure maple syrup. So half a gram of syrup or half a gram of any kind of weight added to that hydrometer could make the syrup apparent density 2 degrees Brix out heavier than it really is. If you're not familiar with the Brix scale, Brix is a measure of sucrose concentration in a pure sucrose solution. So if you had 50 Brix liquid, it would be 50% sucrose. We know that there are more things than sucrose in maple sap and syrup, but it's close enough and it's used as an estimation for sugar content in syrup. So just to revisit this, half a gram of weight artificially sort of adding or hanging out on that hydrometer can make a 2 degree Brix difference in the apparent density of syrup. And for reference, the entire range of legal density syrup is 2 degrees Brix. So that's 66.9 to 68.9 Brix. So just half a gram, which is equal to about 6 drops of syrup hanging out somewhere on that hydrometer, pulling it down, can give a completely different reading for the density. So we know that maple syrup has good flavor. A lot of folks like it, a lot of cultural heritage behind it, and folks have their preferences, but not every drop of pure maple syrup meets the standard. And we know that both firsthand and through our work talking with producers and hearing about the issues. And collectively, when syrup does not meet the standard, they're called off flavors. And we've talked about off flavors in 2 broad categories: Mother Nature off flavors and processing off flavors. And I'll go through each larger class of off flavors and then give you an example of each. So Mother Nature off flavors are really the result of natural changes in the sap chemistry, and either through the tree's response to its environment, the weather during the sugaring season, or broader changes in the climate in which it's growing, can have impacts on the precursors for flavor and color that are in solution in that sap. Broadly speaking, Mother Nature off flavors are things that just happen because they happen. It's not necessarily something producers did wrong, but they are things that can impact syrup quality. The three most common Mother Nature off flavors are called metabolism, buddy, and sour. We won't get into too many of them, but we will talk about buddy. Buddy tends to appear, this is using the quotes, buddy is a term that's used for this particular flavor. It appears near the end of the season, but it's not tied to a specific stage of bud development or phenological stage. So you can't use binoculars and look up at the crown of the tree near the end of the season and say, yes, I'm going to make buddy today, so I'm going to stop. It's really more tied to unseen forces and a lot of communication between the below ground parts of the tree and the above ground parts of the tree as those uh, uh, signals about whether or not it's time to break dormancy or not are being transferred throughout the plant. So we know that it involves the end of the season and the breaking of dormancy, but there's still some unknowns about the physiology, about particularly how it's happening and what triggers there are. If you were to taste some of this syrup, it would have a Tootsie Roll, chocolatey, maybe a cabbagey or sort of a sulfury taste. And all off flavors can be on a spectrum of intensity. You can have mild ones, or you can have very strong ones. You can have combinations of off flavors. And some of my work is helping producers diagnose what they have if they can't figure it out themselves, and trying to figure out where those issues are. And then on the research side, we try to figure out, okay, how is there a way to mitigate these flavors, or are they just destined for another market beyond grade A pure maple syrup? Some colleagues in Quebec have done quite a bit of chemistry research on the precursors and the materials involved in buddy off flavor. They tend to be associated with sulfur compounds, and they can show up and can be detected at relatively low concentrations by tasters. The larger class, or not larger, I should say, the other class of off flavors are called processing off flavors. These are things where the producer either, well, hopefully not intentionally, but the producer did to impact the quality of the syrup. And this could be the result of a mistake in manufacturing the syrup, or just not understanding the instruments and the equipment needed to produce syrup. And the picture on the right, I'm not citing a paper that I wrote. I'm actually citing some burned syrup that I made in 2021. So there's a saying in sugaring that there are two types of sugar makers. There's sugar makers who burned their pans, and there's liars. So there's just only two types. So I'm totally admitting to burning a pan here. Processing off flavors, they can be frustrating, they can be damaging to the expensive equipment, but more often than not, you can figure out what went wrong and help alleviate the issue in the future. This picture here on the right is maple syrup with what's called a ropey defect or ropey off flavor. And you can see it's not actually syrup anymore. It's this really stringy material that has these long polysaccharides where a bacteria, a specific bacteria, has converted some of the sugars into these long stringy materials. This is kind of a combination of Mother Nature and processing. This is where the sap quality got to a point where you weren't going to make good quality syrup. And if the producer took the time and actually made the syrup, they obviously didn't identify that it was an issue. And so poor sanitation, holding on to the concentrate too long. And again, I'll take ownership of this slide right here. It's some ropey syrup that we had an experiment. We were boiling concentrate. Something conspired. We weren't able to boil it right off the bat. Had to wait a few hours overnight and boiled again. And we ended up with this lovely picture, which is kind of the only economically valuable part of that day's work. So consumer packaging is also quite important. And so you're taking this good quality syrup, you've done all the work, all the effort, all the money and expense and time to make it, then you're hoping to deliver it to a consumer in a form that they expect. And so a lot of times that is in a relatively small consumer package, perhaps a plastic jug or a glass bottle. But doing that process of hot packing that syrup is really critical. So you can have otherwise good syrup put into consumer packaging and have a defect. So you need to you need to heat that syrup up to between 180 and 190. And you have to understand that not all of your packaging is going to be as good at maintaining quality. Some work that I did along with my colleague Mark Canella, we sampled a lot of retail syrup, so consumer packaged syrup that was in the marketplace. We purchased over 200 containers. We measured the basics of color, clarity, density, and flavor. And perhaps not surprisingly, we found some defects. The number one issue was color. And we do know that over time, especially if exposed to oxygen through perhaps a porous material or relatively porous material like plastic, we will see darkening over time. We also saw that the flavor results, there were defects in flavor. In fact, we found defects in all 4 of the standards of grading. I won't get too into the data here, but I do want to say that color was the number one thing. We think some of that was just producers not understanding the rate at which syrup darkens, and perhaps not checking or having enough control over when that syrup is packaged and when it eventually reaches the consumer. Some of it was on us. There was a delay due to COVID, so we couldn't sample the grading of that syrup right away. But even if you account for the natural rate of darkening, we were able to use some results from Tim Perkins' work. We were able to back calculate. We know that a good chunk of that syrup would have been out of grade for color anyway. We did see some results in flavor. We found that it wasn't equal across the 2 grades of golden and dark. We saw a higher proportion of off-flavored syrup in the dark samples. And this could be an issue of producers not fully understanding what good tasting dark syrup is and lumping in some what would normally be seen as a defect in with a broad category of dark and very dark syrup. So as part of the Extension Maple program, I'm deeply involved in training and education, both with, like on the right, there's a picture of me and some high school tech center students who are involved in the forestry program who also produce maple. So we're sitting around tasting syrup. Not surprisingly, I bring some bad tasting syrup for them to learn about. And on the left is actually a picture from just yesterday. We did a 1-day full day training on syrup quality as a partnership with Humane Extension and the International Maple Syrup Institute. There's a huge amount of interest in syrup quality. We know that the marketplace has quite a bit of syrup that's out of grade. Some of it is just a little too dark for the grade, and some of it's actually, unfortunately, has bad flavor. So producers are aware of that. They want to improve the product they can give to their consumers, and they're seeking out trusted research-based knowledge to get that training. Another bit of information they can take advantage of, I just launched a second set of what I'm calling the maple syrup off-flavor reference set. And this is a series of 4 samples of syrup that represent sort of a middle-of-the-road example of each of these 4 off flavors: scorch, ferment, metabolism, and defoamer. And this is an opportunity for people to taste these standard flavors and then discuss it within their operation, and hopefully avoid making it in the future, or at least if they make it, making sure it doesn't reach a consumer in a retail package. And that's all I have. That's a lot to cover. So I really appreciate, I know Abby does, the opportunity to share all that information, and never hesitate to reach out in the future if you have questions.
Fantastic. Thanks, Mark. Thanks, Abby. I was just watching along and didn't even look at the time, so I apologize, but we only have a few minutes left. So perhaps 1 or 2 quick questions from anybody in the audience. Scott's wondering, is hot doggy an off flavor? I don't know. It's a great question.
Yep. Mark alluded to our new project that is, and I skipped over my slide on it. We have a project to characterize both chemically and organoleptically the characteristic flavors and off flavors of maple syrup. So Andrew, we will definitely be investigating hot doggy as a standard profile, both from a chemical and organoleptic standpoint.
Thank goodness.
Coming
All right.
soon.
Happy to hear that. The people were wondering. Perhaps in that same vein, Dr. Parisi, go right ahead.
Oh, Leslie, please.
Sorry, Leslie.
Anyway, great talks, both of you. So I have one question each. Let's see, Abby, when you were talking about why don't the trees explode, I expected you to say that, well, because there's sugar in the water, it's lowering the freezing point. But that, how much is the freezing point lowered by 2%? And I don't want to put you on the spot if, just.
I don't know the exact number, but it is not super substantially lowered by the 2% sucrose. It is lowered. I mean, that's one of the reasons it's there, is to help lower that freezing point. So that's a great question. And I think somebody put in the chat the great April Fool's NPR episode about exploding trees. So hopefully check that out on your flight or before your flight while you're at the airport. It's fantastic.
Oh, okay. And then for Mark, when you were talking about the hydrometer and it being thrown off, that sounds like an opportunity to invent something better, or I mean, is there an entrepreneurial opportunity there? If
Sure. Yeah. I mean, hydrometers are widespread. They're relatively affordable and they can handle the hot temperatures of syrup in the moment of production. And so anything that you would invent would have to accommodate those hot temperatures in the moment. You can use refractometers, which use a totally different
I want to
process.
ask about that because
Yeah.
when back in the day when I was using sucrose gradients, I used a refractometer. Yes.
Yeah, the problem is you need a tool that producers can use at temperatures 200 degrees Fahrenheit to 220 or 30. And
Wow.
refractometers, really, even temperature compensated ones, are not really manageable at those temperatures. But room temperature, absolutely. Refractometers are a far superior device. Hydrometers, I definitely wish there was something a little bit better to be used, and I suppose there could be. But you have to overcome that issue of the moment of production, and it has to be relatively easy to use.
All right. Well, thank you, both of you.
Sure. Any other questions?
I did see one that Hans asked in the chat about the rate of sap flow between different trees. And that Hans is, Mark and I will both take a stab at this and say different things and not cover everything. There's so many different factors that can control the rate of flow or make the rate of flow, sap flow, different from one tree to another. A lot of it can have to do with just basic size and the thermal dynamics of what is actually freezing and thawing in that tree. So I'm going to go with that one as my big one. And if Mark wants to add anything else.
Well, I would say the rate, absolutely agree, but I would also say the rate isn't as important as the total yield. So you might have, there's still this folk wisdom of always tap on the south side of the tree because you end up with more sap. But what is most likely the case is someone taps on the south side of the tree, sees a lot of sap flow or rate, but never measures every single drop over the course of the season, over multiple seasons. So you could have a year where it's really disadvantageous to have those taps on the south side of the tree. So I think where the tap is relative to the sun exposure is important. If you're tapping into good clean wood, or if you tap into some slightly stained non-conductive wood, that could also be an issue.
Thank you.
Vern asked, are there rules about bourbon flavoring and other alterations in the process?
Yeah, it's a good question, Vern. Bourbon barreled syrup or any other flavor infused syrup would not fit the definition under the current grading standards for grade A pure maple syrup in either golden, amber, dark, or very dark. It would have a defect, even though presumably people are doing it to get more value or more money for that product. The standards that are in place now really predate this growth in this segment of maple. And so I know that there's interest at the state level, probably less so at the USDA, but definitely at the state level, they're interested in revisiting those standards and trying to find an accommodation. But yeah, it would definitely be seen as a defect, even though, some of them are pretty tasty.
I know I enjoyed the bottle of bourbon maple syrup that came from the Proctor Center last year, and it was really, really tasty. Well, we've gone a couple minutes over, so I think I'll call it there and say thanks again. Thanks once again to our speakers. And keep an eye out for next month. On June 15th from 1 p.m. to 2 p.m. we have a talk entitled Growing Stuff with Ann Hazel Rigg and Vern Grubinger. So we're looking forward to that as well. And thanks everybody for coming today. We appreciate it.
Thanks, everybody.
Thanks, everyone.
Thank you.
Bye-bye.
Bye.